In this chapter, we will be studying sequences and series. In this lesson, we will be studying geometric series.
Alright, hi everybody. So in this lesson here, we're going to take a look at geometric series. Okay, now remember that that in a geometric sequence, to go from one term to the next in that pattern of numbers, you are multiplying by some common ratio. Well, now as we saw with the arithmetic series, what we're going to do with a geometric series is we're just going to add up all of the terms in that particular sequence. So 3, 6, 12, 24 forms a really small little geometric sequence where we're multiplying by 2 every time. As soon as you switch those little commas that would be in there with addition signs, it becomes a geometric series. Now, in this course, you really just need to know what the formulas are for adding up the terms of a geometric series. But you know what? I'm going to quickly just show you how we get to that result, merely because it's very similar to what we saw with that supposed story about Gauss as a child doing this. So I'm just going to show you how we do this, come up with this, the sum of the terms in a geometric series. So first of all, I'm going to write Sn here, and I'm going to write out the terms in that geometric series, starting with our first term. And then remember, to get to our second term, we're going to multiply by r. And then to get to the next term, we're going to multiply that t1 by r squared. We just keep multiplying by r. And we keep doing this, okay? And our last term is going to be, or sorry, I should say our second last term is going to be t1 multiplied by r to the n minus 2. And then we multiply by one more r, and we get t1 multiplied by r to the n minus 1. And that was the, if you remember back, that was the general term of the geometric sequence. So it becomes the last term of this particular sequence when we write it out like this. Now, what we're going to do, similar to what Gauss did, or again, who we think did this, we're going to write out this entire sequence again, but the twist is, in this time, what I'm going to do is I'm going to multiply by r. Okay, I'm going to multiply every one of those terms by r. Now, watch what that does here. That takes this t1 term and actually makes it t1r. t1r becomes t1r squared. And that's going to happen all the way up here. I'm going to get a t1 r to the n minus, whoops, sorry, I wrote that out wrong, r to the n minus 2. I did it again, I don't know what I'm doing here. R to the n minus 2. Now this was my t1 r n minus 3, and then I multiplied by another r. Then when I multiply t1 times r to the n minus 2, add another r, add another 1 to the exponent, becomes t1 r to the n minus 1. And then when I multiply t1 r to the n minus 1 by r, I get t1 r to the n. Okay, now all you got to do, if you're having a hard time figuring out what I just did there, just think about every time every time I multiply by r, I add 1 to the exponent. Okay, so n minus 2, if you multiply by r, n minus 2 plus 1 becomes n minus 1. N minus 1 plus 1 becomes n, okay? Now the trick is, what we're going to do to figure out what the sum is, we're going to take that first term and we're going to subtract the second term. So I'm going to get Sn minus Rsn on the left-hand side. We'll come back to that in a second. Now, T1 up here does not have anything that's like it in that second line there. So T1 kind of pops out here, but T1R minus T1R cancels. T1R squared minus T1R squared cancels. In fact, I've written this out here so that you're going to see all of those terms cancel. The only one that doesn't cancel is this t1 r to the n. So this is what we would call it like a telescoping sequence here. All of these things cancel. All we're left with is that first term and that last term. And actually this makes things a little bit easier here because I can factor out the Sn on the left-hand side, 1 minus r. I can factor out the t1 on the right-hand side, t1 times 1 minus r to the n. Then I can divide, and the sum of the first n terms of a sequence will be t1, 1 minus r to the n over 1 minus r. It's kind of cool that works out so simply like that. Now, you're often going to see them factor out a negative out of numerator and denominator and just switch the terms around. So often you're going to see it written as t1 multiplied by r to the n minus 1 over r minus 1. Okay? Anyway, and when I go back to my workbook here, you'll see that that's exactly what we've got written here. So T1 is the first term, n is the number of terms in this finite series, r is the common ratio, and Sn is the sum of the first n terms. Now, another way of doing that really is to go, well, essentially to go back to my sheet here and to leave it like this in the first case here, right? If you think this one through here, I got this one, I got that term, and now this is going to take a little bit to kind of follow along here, but there is another formula for this. I'll maybe write this over here. I'm going to write this line out again. Sn minus Rsn is going to equal T1 minus, now I just want to think, where on earth did that T1 r to the n come from? Well, it came from right here. And I got that by multiplying that by r. That is where that T1 r to the n came from. It was this term multiplied by r to get this term. Now, so I'm going to write that out a little bit differently because I know based on the previous lesson that this is actually the general term of a geometric sequence. That's Tn. So I multiply Tn by r. Now, factor out the Sn on the the left-hand side. Divide, and I will get Sn is equal to T1 minus Rtn over 1 minus r. There's the other equation that we're going to look at. Or you can factor out the negatives and make this Rtn minus T1 over r minus 1, if you will. It doesn't really matter how you set that up. In the workbook here that we've been working from, they set it up as Rtn minus T1 over r minus 1. It doesn't matter. But notice that just like it was with arithmetic series, we've got two different formulas right here. This one, I don't need to know what the last term is. I don't need the last term, okay, or the Tn. But here, I do need Tn, or the last term. Now, actually, from this point on, really what we're doing here is just working through problems, and I want to show you kind of several different ways these questions could get asked and things you got to look out for. So let's do some examples. All right, so for our first example here, we're being asked to find S sub 7 for the sequence, the geometric sequence that starts -3, 6, -12. Okay, well, first of all, I noticed by my notation here that I'm being asked to add the first 7 terms together. I can also tell that my T1 is going to be -3, and then by doing my quick division here, the second term divided by the first term, I know that r is going to be -2. Now, don't leave off the fact that r is negative here. This is an alternating sequence. That's going to be important. Okay? So now I don't know what the last term is, so I'm going to use the formula Sn is equal to T1 multiplied by r to the n minus 1 over r minus 1. So now S7 is going to equal the first term, -3. And I'm going to put that in brackets because of that -3 there. I don't want to make a mistake with that. It's going to be equal to r, which is, sorry, not r, which is -2, to the 7. And again, I'm putting parentheses around the -2 because I don't want to make a mistake with that. If I don't put the parentheses in front of that -3, that's actually not that big of a deal in this case. But if I don't put the parentheses in front of that -2, that will be a big deal here, okay? Or at least it can be. In this particular example, it actually won't be. But that's not to say that if you get used to not doing that won't become a problem later on here. The issue is that this is an odd exponent, so it's not really going to affect the negative. But if it was even, yes, it would. Now I'm going to subtract 1, close the parentheses, divided by, and then in parentheses, -2 minus 1 down in the denominator. Now, that just becomes calculator work. And I'm just concerned that everybody is using the calculator correctly here. But anyway, let's walk this one through. So that is going to become -3, and then we're going to multiply that by, and I'm going to put parentheses around the entire numerator. -2 to the power of 7 minus 1, close parentheses for the numerator, divided by, open parentheses for the numerator, -2 minus 1. Now, I'm going to press enter here in just a second, but I frequently get the the case here where people will be following along with me. I'll do this sort of thing on the board. They'll say, I did exactly what you did, and I'm getting a different answer. What's going on here? And then invariably we come back to the calculator and no, they're not doing exactly what I did. They're usually forgetting a set of parentheses. Please make sure you're using an adequate number of parentheses here. There's parentheses around the numerator, around the denominator. There's parentheses around the base of an exponential, or the base of a power if the base is negative. Please watch that. Press enter, and I get that the sum is negative 129. Okay, let's take a look at this next one. Find the sum of, okay, now notice in this case here, I don't know how many terms there are. That's actually not given to me. Now when we were working with arithmetic series, that actually would have been an issue. I would have needed to figure that out before I could find the sum. But in this case I actually don't. I know that my first term is going to be 4. Okay, I know that the nth term, whatever n turns out to be, is going to be negative 8,748. Now bear in mind, that is not the sum, that is the last term. And then I also know, if I divide that negative 12 by 4, that r is going to be negative 3. So I can use my second equation there. Now in this case, I got to use Sn, Tn minus T1 over r minus 1. And I don't know what n is, so I got to kind of leave that like that is. So parentheses around the numerator, parentheses around the r, and then parentheses around that negative 8,748, because I got to make sure I'm treating those negatives correctly. Minus T1, now T1 was just 4, so I'm okay with that, divided by brackets around the denominator, and then negative 3 minus 1. Now in this down here in the denominator, it's not so important that I put that negative 3 in parentheses, but let's just be consistent here. So now, let's go to our calculator. Whoops, getting a bit of a glare there. So that will be, in parentheses here, the numerator, negative 3, negative 8,748, okay, minus 4, close the parentheses, divided by, open the parentheses, negative 3 minus 1. Whoops, and now you can't see that. I'm sorry, we're getting negative 6,560. Negative 6,560. Now hopefully you're getting the right value. If not, please again have a quick look at what I've just entered into the calculator, and let's make sure that what you're doing lines up with what I've got there exactly, okay? Because again, oftentimes, almost always, it's an issue with parentheses. Okay, let's do a few more here. Determine the sum of the series. Okay. Let's take a look at that. What are we doing here? Well, now notice this is very similar to that last one that we did. I know T1 is 160. Whoops. I wanted to write something different there. 1 over 64. I know that Tn is going to be 1,024. Okay. Still, I don't know how many terms there are in the sequence. I could figure that out, but because I'm asking for the sum, I don't need to. R is going to be the second term divided by the first term. So it's going to be 1/16 divided by 1/64. So it's going to be 1/16 multiplied by 64 over 1. So 64 divided by 16, that's 4. So my R value here is going to be 4. So Sn is going to equal Rtn minus T1 over R minus 1. Again, I don't know how many terms there are in this sum, but that's okay. That's going to be 4 multiplied by 1,024. Oh, now I'm going to put parentheses around the whole numerator. Okay. I don't really need to put parentheses around the 4 because it's not negative, but I need to multiply that by 1,024. And so putting parentheses around that, the calculator will understand that. Okay, minus T1, which will be 1 divided by 64. All over 4 minus 1. So Rtn minus, T1 over R minus 1. Let's go to the calculator here. So in parentheses, 4 multiplied by 1,024 minus 1 divided by 64. Now closing brackets for the numerator, divided by, I'm going to open brackets for that numerator again, 4 minus 1. Didn't really need to do that. I could have done that in my head, but anyway. Whoops. Press enter. Okay, and we're getting this weird sort of a decimal here. Oftentimes, we're going to see if we can put that into like a nice fraction. So let's press fraction, the math button, go to the fraction. Ugh. Okay, well I'm getting kind of an ugly fraction. 87,381 over 64, which is approximately equal to 1,365.3. Okay, that was a little bit of a crazy number, but that's okay. But the reason why it's looking like that is because up here, look at the first few terms here, 1/64 plus 1/16 plus 1/4. We're adding fractions together, and eventually you're going to see that this is going to get large enough that we're not going to be working with fractions anymore. We're going to be working with larger numbers, but that fractional part remains. 4. How many terms are in the finite sequence 2, 4, 8 2 plus 4 plus 8 plus 16 plus so on, blah, 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 if the sum is 4,094? Now, really important that I point this out here, because anytime this question gets done, there's usually a large group of people that treat that as if it was the nth term, and it's not. That is the nth sum. 4,094. I don't know how many terms there are in the sequence, but I know what the sum is in this case. I also know what the first term is. It's 2. And then if I divide the second term by the first term, third term by the second term, I get that my r is equal to 2. But I don't know how many terms there are in the sequence. I don't know what the Tn is. I don't know the last term. So I'm probably going to use that first formula that I looked at here, okay, which was going to be T1 r to the n minus 1 over r minus 1. Okay, so I'm going to get 4,094 is going to equal T1, which is 2. R was 2, so 2 to the n. N is what I'm looking for, minus 1, over, 2 minus 1. Well, part of me kind of really likes what I'm seeing here, because the denominator was 2 minus 1. Well, that's just 1. So right away I can write that. That's 4,094 is going to equal 2 to the n minus 1. So I really like that. Now I'm going to divide both sides by 2. So I'm going to take 4,094, I'm going to divide that by 2 and see what I get here. And I get 2,047 is going to equal 2 to the n minus 1. Okay. What I'm trying to get here is I'm trying to get n. So let's move that 1 over. So that'll be 2,048 is going to equal 2 to the n. Now, I am really hoping that 2,048 is in fact a multiple of 2, or a power of 2. If it's not, then what I'm going to have to do is go to my calculator and graph both sides of the equation and look for that intersection. Now, it turns out though, I don't have to play with my powers of 2 all that long to realize that this is in fact a power of 2. I know off the top of my head that 2 to the 10 is 1,024. And so when I look at that a little closer, 2,048 is really just 2 to the 11. So that means, therefore, if 2 to the 11 is the same as 2 to the n, I know that n must be the same as 11. So there are 11 terms in that series. Okay, next one. Remember the clever child who convinced his mother to only give him a penny for his allowance, but that she would have to double it each week? If he saved all of his allowance, how much would he have in 12 weeks and then in 30 weeks? Okay, those are the 2 parts of this question. So this is now a total. We're not asking how much is he getting in a specific week. If he just saved everything, how much would he have in 12 weeks? Okay. Well, we know that the first term is a penny. So let's make it 0.01. We're doubling it each week, so let's make r equal to 2. Now, there are 2 questions here. I'm asking where n is equal to 12, and then when n is equal to 30. Okay, so 2 separate questions here. But that's all I need. Okay, that's all I need. This just becomes calculator work here. So I'm going to use my first formula. Sn is equal to T1 r to the n minus 1 over r minus 1. Now, S12 is going to equal a penny multiplied by doubling 12 times minus 1 over 2 minus 1. And just like it was in the last time we did that, 2 minus 1 is equal to 1. So the denominator is actually not even all that necessary here. So it's really just 0.01 multiplied by 2 to the 12 minus 1. And we're going to get $40.95. Now that's a little underwhelming, really, when you think about what we were looking at before here. But let's take a look what happens at the 30th week. If he saves all his money up until the 30th week, now that's the sum of the first 30 terms. So 0.01 multiplied by 2 to the 30 minus 1 over 2 minus 1. Now again, the denominator is kind of going away on us, so that's not that big of a deal. So all I really got to do is change that exponent to a 30 and see what happens. Well, between the 12th week and the 30th week, you go to your calculator, there is a substantial improvement in his financial situation here. By the time he gets to the 30th week, he will have saved $10.7 million. Okay, so even though, once again, with geometric sequences and whatnot, we see a very, very slow growth up front, man, it starts to go fast in a little while. Unbelievable. All right, one last question here. It says, a particular oil well in Alberta produces 46,000 barrels of oil in 2015. Each subsequent year, production drops 3%. Okay, now we've seen a question like this before. Let's think about that. When I say it drops 3%, what's left over? And that suggests to me that my R value is going to be 0.97 or 97%. Well, that's a little hint there, so just watch out for that. So now the question is, how many total barrels of oil will the company expect to remove from this well by the end of 2025? We're going to answer to the nearest barrel here. Okay, well, T1 is going to equal 46,000. Okay. There is a bit of a trick here because 46,000 barrels came out in 2015. Okay. I'm trying to figure out how many, not how many years went by. That would be a mistake. Because when we get to 2016, everybody, 2016 is the first year later. And if we go 2016 minus 2015, you're going to get 1. But 2016 is the second term. Not the first term, it's the second term. If we went to 2017, 2017 minus 2015 is 2. But 2017 is actually the third term. 2015, 16, 17. So even though 2025, if I subtract 2015 from that, that's 10. That's the number of years later that it occurred. But we started counting at 2015, so we have to include that number here. That's going to mean n is actually 11. And I promise you, there are going to be all sorts of people that are going to get so close to the right answer on a question like this, but because they forget that the number of years does not match up with the way we're numbering the terms, there's going to be a mistake. So again, just to illustrate what's going on here, here's 2015. That is term 1. 2016 is term 2. 2017 is term 3. Now, this is no years later. This is 1 year later. This is 2 years later. Okay? By the time we get out to 2025, this is going to be 10 years later, but that has got to be the 11th term. Okay, and if you just follow that through and count that out, you'll see that what I'm saying is correct here. Okay, so now we know where we start, we know how many terms are going by, and because we paused partway through this question, we already know that R is going to be 0.97. Okay, so the sum of the first 11 terms is going to be 46,000 multiplied by 0.97 to the 11 minus 1 all over 0.97 minus 1. All right, now that is just calculator work. Okay, so we've got 46,000 multiplied by 0.97 to the exponent 11 minus 1 divided by, and I got to put this in parentheses here or else the calculator is going to think that I'm entering in something else here, 0.97 minus 1. Press enter, and we're seeing 40, what is that? 436,530. Now it says 7.8, but the question says round to the nearest barrel. So 436,538 barrels. Okay, and there you go.